So hello everybody, and good morning, good afternoon, and good evening, depending on where you are in the world. So I would like to start thanking the organizers of Ivara 2020 for making the effort of organizing this online event so quickly. And I'm sure that this gave the opportunity for a lot of people in our community of neutron stars and nuclear astrophysics to be able to attend. It wouldn't necessarily be possible in front situation. So today I'm going to talk about twin stars, and I'm going to present work that was done at FIAS in Frankfurt. So I'm going to start with the people that are part of this collaboration, which are Dr. Steffen Schramm, as well as Veronica Dexheimer, which is not part necessarily officially of our group, but is a very present collaborator. And our two master students, Pia and Parit, and also our collaborators, Sophia Hahn and Prashanta Shah. They are in Ohio University and also in Ferrara University. So, as you may know, Dr. Schramm passed away last year, and this was an immense loss to our nuclear astrophysics community. So I'll be presenting the last works of our former group of astrophysics at FIAS. And also our former students, Pia is now in Melbourne in Australia, and Parit is joining the University of Cologne here in Germany. So I will start with talking about phase transitions and a little bit of our outline here, and then I will continue with an overview of twin stars and then discuss how microscopic and macroscopic properties can give rise or suppress this kind of configurations of stars, and then I'll draw my summary and discussions. So I'll start with the topic of deconfinement phase transitions in nature, which has been a topic of extensive study in the QCD, and which is summarized here in this diagram. And so here in this diagram, it is displayed the different states of matter, both confined and deconfined as well, in different ranges of temperature and densities, as well as isospin. And we can see that the neutron stars lie here in this regime of low temperatures and high densities, which are not reached in any laboratory on Earth as the ones that we are seeing here. And also are the objects that appear also in the isospin plane as well. So so given that we don't know the equation of state of nuclear matter, so this is still an open question, there are a range of possible solutions for this scenario. And these are the ones that that's why we have like a range of possibilities here. And some of those ranges lie in this region where the confinement phase transition can take place. And for talking about twin stars, we will be talking about specifically hybrid stars, which are configurations which can have both hadrons and quarks as well. So, of course, each of there are several models in the market at the moment that propose to explain the equation of state of nuclear matter, and each of those models will give rise to a different family of stars, which we can see in this image here to the right. And then in this case, this is a range of possible masses and radii. There are configurations of stable stars depending on their central densities of each of those stars. So twin stars are directly associated with the concept of a third family of compact stars, which is illustrated here in the top left. So in general, compact stars have ranges of possible masses and radii, which are those families that I mentioned before. And the way that we dictate how these curves or these families are formed is through their equation of state. So here in this image, the red curves correspond to the ranges of unstable configurations, and the black curves are the ranges of stable configurations. And so in the range of unstable configurations, these stars will usually, like for neutron stars, they will usually be unstable and eventually collapse into a black hole. So in the case of white dwarfs, which are those one here to the right, there are a family that is very well, there is a family that is very well defined, which this is because we know the equation of state of white dwarfs, and these are stars that will have like much higher radii and masses more or less the same as for neutron stars. So now, if the second part here would be the neutron stars, and if we allow for a third phase transition, then it is possible, and that's the main scenario that we are discussing here in this talk, that a third family can appear, and this would be a new branch of stable stars in which those stars are hybrid, and therefore they have an amount of quarks present in their interior, and this is basically what gives the rise of a twin star configuration, so to say, which would be the case in that we have the same mass for two stars. So for example, we can look here, and this would be two stars with the same mass but completely different configurations. So for example, we could have stars that are hadronic, as is displayed here, and in this branch, and in this other branch here we could have stars that have a hadronic outer part, but in the core they have an amount of quarks. And this is important because this, if we find in nature two stars that would be classified as neutron stars, and we can identify that they have more or less the same mass and really different radii, we can infer that this is a signal for quark matter. So determining the existence of these objects or observing these objects would be a signal for the existence of quark matter. And just to illustrate this, we can also see in terms of stability here. So here's just a plot, similar plot as this, but as in mass as a function of central density. And then the stable branch would be this part here, and then also this part here, which would be corresponding to this part here and also this part here. So when it comes to modeling these objects, twin stars are modeled as in the same way as we model neutron stars. So we basically have two ingredients, which are on one hand solving the Einstein's equations, and on the other hand giving an input of an equation of state, which will give the energy and pressure in the energy momentum tensor, which is represented by the Einstein's equations here. And so in these two ingredients that we have, an important part is the equation of state, which for twin stars will be an equation of state that is hybrid. And so we will have on one part an equation of state for hadrons, or another part an equation of state for quarks, and this will be connected through a phase transition, which in this case is going to be a sharp phase transition. So from this connection and solving the equations of our hydrostatic equilibrium, we have four possible scenarios that are illustrated here, and this is from the work from Alfred and Sophia. So here we have in the A scenario, a scenario in which, like in the green curve here, we have the hadronic branch, and then at the moment that quarks appear in the red part, the dotted represents the unstable branch. So the moment that quarks appear, they make all the family unstable, and then no twin stars or hybrid stars are possible. So there is also the scenario in which you have hadronic stars, and then you can have some stars that have a little bit of quarks in their interior, but then it goes unstable, but then goes stable again. So we can also have the case in which we have hadronic stars, And then we have stars with quarks as well, but then there's never a third family or twin solution. And we also have the case that we have only hadronic in one branch, and then a branch of part of unstable, but then in the new branch we have only hybrid stars. So in these four scenarios, only those two here, the B and D, would correspond to twin stars configurations, and the other ones would be just like only hadronic and also hybrid, but no, in which no twin star configuration are possible. So moving on, of course, when we model these objects, we have to take into account the observational constraints. And so we have the most recent observational constraints come from the high mass neutron stars that were observed thanks to the Shapiro delay techniques that allow us to measure the masses with very high precision. And we also have, of course, the nuclear properties with the ranges that you see here. And we have also the most recent results from LIGO and Virgo, in which the total deformability of the tidal deformability of the stars due to the gravitational pull was estimated, and then we have those values here as well. So I mean, in the last years, there has been a lot of effort from our community to understand how twin stars can appear in nature, also mostly in terms of the equation of state. So for example, we have some efforts regarding the trying out different models, both in the hadronic side, such as, for example, the chiral model here from Dexheimer, and also the quark models, such as the NGL from Blaschka's group. We also have tests of the nuclear properties, just trying out different properties, such as the effective mass here that is displayed in the work from Christian and Schaffner-Billig. And we even have, in some cases, the work from Alford and Sudrakian, in which they tried different transitions, not only to quark matter simply, but also within quark matter, such as to CFL. And then in this case, you don't not only find a third family, but you also find a fourth family and so on. So this is also some of the efforts that are being taken. So when we go more specifically into the microscopic aspect of twin stars, of how they are created or how they can take place in nature, this will base the main ingredient for this will come from how stiff the equations of state are, both from the hadronic side as from the quark side. And of course, like the hadronic side, it has to do with the nuclear properties at saturation that are fixed, as well as the different parameters that we have that will be associated with this, but like also the stiffness at higher densities and so on. And for the quarks, it will be basically associated in terms of stiffness to the sound, speed of sound, or the vector interactions, which would be equivalent. And basically, how stiff those equations are or how soft those equations are, though this relation between these two equations of state, when they are matched, will have an impact on where the critical point is going to be. And this critical point can be summarized here in this image in terms of thermodynamic properties, such as the critical point of in terms of pressure, for example, or chemical potential, and the energy gap. So, for example, in this work here from Gloria and Rezola's team, they analyzed specifically for one model how these different scenarios could these different scenarios of hybrid and twin stars could appear in terms of the space of parameters, which here is the energy gap and the critical pressure. So of course, this is specific for one model, but can be done thoroughly for other models. And this was done already in the past for several models and also several parameterizations as well. So, so looking closer into the constraints regarding twin stars, we can first look into the possibility of twin stars in terms of maximum mass. So we have the constraint of 2 solar masses or more than 2 solar masses now. And so basically here I'm showing the work from Pia and our group in Frankfurt, which was using the chiral model and the VMIT model as well, or VBAG model, depending on how you want to call it. And in this case, we are showing that if we fix the hadronic model, which here we are using only one, and play around with the parameters of the quark phase, we can see that by softening or stiffening the equation of state here, for example, just by changing the vector interactions. So if the equation of state gets more stiff, this will be the transition point will be shifted to higher densities. And if you reach too high densities, you will reach a point where you don't have stable solutions anymore. And on the other hand, if you also soften the equation of state, then you have values of radii that are more compatible with the tidal deformabilities. There are also another constraint, but then you only reach very low masses. And you can, and if you have something in between, if you have maybe not so stiff and not so soft, you can have something in between. But this is still the case that you have, you can find twin star configurations, but only for low mass twins. So, so this is one point to take into account when you play around with the quark phase. If you have two stiff equations of state, you just don't have any stable configurations. And if you have too soft, then you just don't have enough stiffness to reach the solar masses. So in another work that we did recently, we did the other way around. So we checked different values of, now here this was with the many body forces model and also the VMIT again. But then here we not only checked the different parameters for the VMIT, we also checked the stiffness of the hadronic phase. And so this is in red here. We have a twin star configuration, which reaches closer to solar masses. But then we have here the same or a similar quark phase, but a way softer hadronic phases. And then for the hadronic phases, we can have phase transitions that happen at lower densities, and they are in agreement with the constraints for tidal deformability. But on the other hand, we don't have we cannot find those solutions for high mass twin stars. So we have transitions that happen at low densities that are in agreement with the tidal deformability, but then we have the same problem of not having high enough masses. So this is regarding microscopic properties and equation of state. So now when you go to the macroscopic properties, we have the solutions of Einstein's equations here in this work. They are coupled to the Maxwell's equation. So this is for magnetic stars. So we are displaying magnetic stars, again, using the many body forces model and the VMIT. And then here we can see two scenarios. One scenario in which here in purple is the equivalent to a magnetic field that is not affecting the star, so like the B equal to 0 scenario, because for this here, you don't have any change for the spherical configuration. And you can see a scenario in which you have, for B equal to 0, you have No, you have twin star configurations, and as you increase the magnetic fields, those configurations disappear. So you have here, for example, as well in blue and in yellow, that this configuration is not sustained by the high magnetic fields. And you can also see the scenario in which you don't have, so here is a bit not so easy to see, but you can believe me or you can check the paper. You don't have a configuration of magnetic field, so you just have a hybrid configuration. So, and as you increase the magnetic field, then, for example, here in orange, then you have third family appearing. And then as you continue increasing, then you have the same effect as in here. And then the magnetic fields end up destabilizing. So basically the message from here is that you can have both magnetic fields creating twin star configurations as well as suppressing twin star configurations. And here we are showing this for, of course, the stars won't have the same radii because they will be deformed and so on, but as in terms of gravitational masses as well. So we have similar effects for rotation. This is work from that Blaschke and this group. And here you can also see something similar in terms of rotation, that in red you have the zero rotation, so to say, like a close to zero rotation scenario, and then you increase the rotation, then you can also see that the twin star configuration disappears. And so this is gives us an important hint that as we know, stars, neutron stars, are born with high rotation rates as well as high strong magnetic field, and this rotation and magnetic fields decay as time passes. And so we can see that magnetic fields can both give rise, and rotation can both give rise or suppress the presence of twin stars in the universe. So in summary, we discussed how both microscopic and macroscopic properties of neutron stars can affect and give rise or suppress twin star configurations. So for microscopic properties, we discussed how the equation of state and how the matching of hadronic and quark equations of state can play a role on identifying how the critical point is important for these configurations, such as, for example, if you have a stiff hadronic equation of state, we can sustain high masses for stars which are in agreement with observational data. On the other hand, we have too high tidal deformabilities, and on the other hand, we have to have enough, soft enough at the transition point equation of state for quarks, so that we have a large energy gap and also a low onset of quarks. Because if you have too many quarks at the phase transition, then it will destabilize the configurations, and then you cannot give rise to quarks, to hybrid stars and to twin stars. So in the regime of high densities, we need to have high masses, but low tidal deformabilities. And a possible solution for this is analyzing a bit thoroughly the crossed vector isovector terms for hadronic models, in which it's possible to have softer equation of state at lower densities, but is still stiff at higher densities. And this is something that is also important, like this crossed terms is something that is also important for the crust. And this is also part of the work that Pardit, our student, is presenting at the poster session. So I really recommend you to have a look. And in terms of microscopic properties, we saw that both magnetic fields and rotation can play an important role on defining how the evolution of stars are going to be, both as having originally twin star configurations that will evolve to non-twin configurations, as well as non-twin configurations that will evolve to twin configurations. But then, of course, we have the cases that we do have spin down and decrease or decay of magnetic fields, but not it's not such a huge change, or the fields are not so strong that enough to actually affect this configuration. So in these cases, the configurations will remain the same, such as in here or in the final lines as well, in the scenarios 1 and 3. So, sorry, scenario 1 and 4. So that's all, and I would like to thank you all and to continue this discussion. Thank you.